So for the presentation of today, I mean for the afternoon, it will be more or less decomposed in four parts. The first one, it will be what I'm going to do about the main principles of SOFA. So as I said, a first part about really all the generic information about SOFA, what you need to know, and also I will show you with Fred some examples to how to build a simulation using SOFA. So a bit of hands-on SOFA. Then we will have several examples of applications that are currently done in the different teams, as I said. So work in progress, I would say more informatic-oriented work. So for example, the live coding that is being done in Lille. And finally, we will conclude the afternoon with some future work about the future of SOFA. We'll tell you a bit more. And so I would say between all these different steps, you can of course ask as many questions as you want. We can discuss things, even maybe test some things together. I think there will be some break in between. We already tested this morning the coffee machine from the corridor. It's very nice. So we can have coffee this afternoon as well. So yeah, discussions I think is important to mention so that it can be interactive at the end of each presentation, so that you can have the answer that you want to have. You can ask all the questions you want. So first, as I said, the first presentation will be about the main principles. I will give you a short bit of context for SOFA, the main principles, how it works, how do you build a simulation, and then we'll have a look at a very small tutorial about it will show you I would say the versatility of SOFA and the way you can easily build some simulation with it. So I'll do this first part with Frédéric, who is just here. We are together from Strasbourg. We belong to INRIA. SOFA, so it's developed at INRIA. And we are together working in Strasbourg around medical simulation using SOFA. So, as I said, we are working about medical simulation. SOFA was at the origin a bit dedicated to that, but it's not at all limited to medical simulation. But I will talk about what we are doing at least in Strasbourg a very little bit. So medical simulation and what we understand by medical and what we mean by medical simulation. It's basically reproducing with a computer, with a simulation, with a computation, what's happening in a human body. So it can be any kind of mechanical, but also thermal or electrical phenomenon that can happen in the human body, even in the pig body when we are making experiments. So what is really a medical simulation made for? It's the first one, the one I would say the most obvious. It's you create a simulation and you then train surgeon using this simulation. There is already some companies proposing that kind of technologies. So that's one application of medical simulation. But not only, we start more and more to see medical simulation. So the simulation, the computation of what's happening in the human body used to predict what's going to happen, what is going to be the result of a surgery, of medical operation. So what's going to be the outcome. So that's for planning, to compute all the different possibilities and the different outcomes of the surgery, to propose then the optimal strategy to the surgeon. And finally, you have also guidance. Guidance is, for example, to add some information of here a video intraoperative information, where you can have also some additional information based on biomechanical models. So where is located the SOFA in all that? That's basically the platform, the software that we're going to use for developing all those different applications. And I would say really the challenge is between training and guidance. It's to make the trade-off between computational efficiency and accuracy. So that's, I would say, the big challenge on which SOFA is focusing. So as I said, we are in the team and in different teams at INRIA. In Lille, in the team Defrost from Christian, in Grenoble as well, and in Nice, in Sophia Antipolis. People are also using SOFA. I would say actively really developing SOFA. You have users around the world, but we are all using this common platform. And this common platform for simulation aims, as I said, at real-time simulation of physical phenomena. I talked about medical simulation, but it can be any kind of simulation. It can be also really mechanical simulation, just basic, not basic in terms of just really mechanical simulation for automobile or any kind of other application. So fluids and electrical phenomena as well. So it's co-developed in these 4 teams at INRIA, and what is interesting to see is that today there is already 4 different startups that are currently being created from SOFA, from previous work in SOFA. And so you have 4 startups using it. We have also industrial users, such as Siemens. And so yeah, so that's open source with the LGPL license and with so more than 150,000 downloads. What you need to know as, I would say, an entry point of SOFA is that it's very flexible. You can really adapt, add the component, so add things and remove things from the simulation very, very easily. That's also one of the reasons some industrial partners are using SOFA for prototyping some computation and some simulation. So I'll tell you, as I said, about the main principles of SOFA and the software. I will start with the software architecture. So it will be relatively basic because without a lot of technical stuff for informatic people. I'm not an informatic guy at all. So it's based on C++. SOFA. You have basically a core which is public, and you have plugins that you can activate or deactivate as you wish, and those are public. And you have also private plugins. You have some work which is then in private repository, where people, that can be you, that can be any industrials or other labs that are developing their own algorithms, their own models that they can develop in private plugin. So all these private core and private plugins, public core and public plugins, sorry, are being versioned in using Git, and you can of course then download it here, and you can see all the information on the website for the download. So then once you download it SOFA, then today at least you need to compile it, but in a few weeks we'll make binaries of SOFA available so that you do not have to compile it anymore. So it will be a first, I think, nice step to go towards a more user-friendly software. So that's, for the moment, you need to download it to compile it. So using CMake. CMake is actually quite convenient for working with SOFA. I mean, for working in such a project, because you can activate, deactivate options very easily if you want to use or not to use any kind of functionalities available in SOFA. You can make shadow it, so have different configuration of SOFA as you wish, and it's managing quite efficiently the dependency. Today, SOFA is compatible with all 3 Linux, macOS, and Windows. And as I said, that's one of the take-home messages. That SOFA, we are currently working on that. We'll propose some binaries of SOFA, so that, yeah, again, making it more easy to use without compilation, basically. So a simulation with SOFA. Now that we saw a bit the basic, how SOFA is built and what is its architecture. How do we make simulation in SOFA? In SOFA, SOFA is based on a scene, so a scene graph. It's describing all the different components that you're gonna use. So you have nodes, and in each node you're gonna describe what you want to simulate. You will have components, for example, the geometry of your object. You will have the model that if we talk about mechanics, for example, you can have a specific mechanical model, mechanical behavior. And all these components, of course, have features. For example, if I take the mass, if we say that our object does have a mass, then the mass density or the total mass of your object then will be one of these features, which are called data. And in SOFA, one of the features which is quite nice is that you can link data to each other, so you can make dependencies in your scene. So let's see. So here is a lever. We don't see it very well, but basically here is the lever. If you want to simulate an object, a deformable object, or even a rigid object, here you will have to define in SOFA a state vector, which is including all the degrees of freedom of your object. Then, depending on what you want to simulate on this object, you can have different kind of degrees of freedom. It can be 1D if we are talking about temperature. It can be 2D if you are making, I would say, 2D simulation, or 3D if you are talking about, a 3D object like here. So it can be, you can have different kind of degrees of freedom defined in SOFA, and those, as I already said, to simulate different kind of phenomenon. It can be here electrical, here fluids, and the idea really with SOFA is to be able to make a multi-physics simulation. So not only mechanics, because it was built at the origin for mechanical simulation, with an emphasis on medical simulation, but again we are moving to a bit more of applications. Then you can, in the case of mechanics, define physical laws. For example, the constitutive law of your object. It can be also the fluid law, or here the way your electrical signal is going to propagate. A mass if you need it, and then you have solvers that are then going to take your system and solve it over time. So how does it look like here? Again, with our lever, we want to simulate this lever. So we have a root node, and then just below we have what's called an animation loop. That's the component that is gonna basically rule the entire simulation. Say when the time step is gonna so when the simulation is gonna move forward, and call the different step of the simulation. So here, if we want to simulate the lever here, we will have to define the degrees of freedom. For example, a constitutive law, as I said, a mass, if you want to assign a mass to your object, and the solvers associated to that. But you can, in a simulation, have several objects simulated separately. So that's the case here. You can have a lever, but you can also have the heart here with completely different degrees of freedom. So, for example, if you want to simulate the electrical phenomenon, the electrical activity of the heart, it can be here a 1D information, and there, if you want to see the deformation, so the 3D position of each point, it will be 3D information. So different kind of degrees of freedom. And so I placed the solver in the same node, but you can also have only one solvers for both objects, depending on the kind of solving that you wanna do. That's one example. One example where you can see that SOFA is really nicely flexible, and depending on what kind of simulation you want to reach, and what kind of choice of simulation you're doing, you can then change that very easily. Basically, move a line just a bit upper here in the description of the scene. We'll see that later. So again, let's take our lever here. So if we want to make this mechanical simulation, we'll have to describe the geometry of our object and assign to it a constitutive law, so the mechanics of the lever. Here, that's hexahedra that are described in the lever. And then you can add many other description, many other representation of this same object. You can have a visual representation, which is quite nice and so on, but absolutely not, I would say, not directly related to this hexahedral shape. We can have a collision mesh, which is here made of triangles, and here it's hexahedra. And you can also have haptic representations, so you can have haptics that is interacting with your models. So all these different kind of representations and interactions that are going to happen during the simulation have to be linked to each other, because if you are pushing on your object, for example, due to an haptic interface, you want this action to have an impact on your mechanical object, on your mechanical representation, but then you want to see your visual model, your lever here, your visual lever, move accordingly to the deformation you applied. So all these different representations are going to be linked to each other, which what we call mappings, and those mappings are connecting together the different representations. So that's something very powerful in SOFA, which enables basically to have different representations of the same object and to have them linked together using that principle of mappings. So an example here, let's say that we want to simulate, I'm taking very different kind of topologies or different representations of this object here, a torus, because it's, I would say, the less obvious case, so that if you understand that, you understood everything basically about mappings. So here, if you take this torus, so it's a torus made of triangles, as you can see here. That's a surface mesh, and let's see that we want to compute the deformation of this torus if we are, for example, pulling on it. But we want to do that for any kind of reason using hexahedral FEM representation. So how is that going to be coupled? Again, as I said, using mappings, you will be able to map the points that you have, I mean, your visual model on the mechanical model that you are really simulating. So all the computation is going to occur on that model and will be then applied on the visual representation. So how does it look like How does it look like? Here I just merged the two representations in the visualization. But what you can see here, you have the triangular representation, which is just purely visual. You have no mechanics on it. But all the mechanics is actually happening on the hexahedra that we saw at the beginning. Okay, that we saw on the beginning, and yeah, all the computation is happening here, but is then applied on the triangular representation, so on the visual model. So that's how mappings are working. I already talked about different kind of topologies. I talked about here the visual model of the torus was made of triangles. The FEM was using hexahedra, so that's what we call topologies. And you have different kind of topologies in SOFA. So when we say loading a topology, that's first loading a geometry. So we have degrees of freedom that we are loading, and the topology is actually how do these degrees of freedom connect together, to connect to each other. So you have, of course, edges, triangles, quads, tetra, and hexa, which are available in SOFA. And again, I just explained, the principles of the principle of mappings, and that's again one of the big force of SOFA, that you are able to couple those different topologies. We saw just previously, the torus, which had triangles, but you are able to map those triangles on hexahedra that are actually really being computed. So that's the idea. For example, you can have you could have a very coarse 3D model of your body that you are simulating, and then having on the surface a very detailed mesh so that you can have a nice representation. That's one example of application of the mappings. There is also work being done currently in SOFA using dynamic topologies. So there is component in SOFA called topology modifier handling the topological changes, and then using those components, then if you apply one topological change, then it's gonna propagate in the simulation graph. So here you could see some videos of work being done currently in the team around all those topological aspects. So maybe it's also a topic that could be of interest for some of you. I don't know if you're interested in collision. SOFA is also proposing collision algorithms. So what is the collision model? As I said, SOFA allows different kind of representations of the same object. One of these representations can be, for example, a collision model if you want to have collision in your simulation. So here are listed the different implemented models, so sphere, triangle, point, line, and oriented bounding box. How does it work? Very briefly, that's in three different steps. The first one, there will be a broad phase. As here, you have bounding box of your object, and the computation will first detect the intersection of this bounding box. Then you will have a narrow phase. Then depending on the method you choose. So here, yeah, so you have different methods available insofar as distance maps, computing the distance of your object to the colliding object, or at least assuming that there is maybe a collision. So distance maps, and then you have the response. There is mainly two methods here. At best of my knowledge, it's not my, I would say, my expertise, my best expertise in so far, the collisions, but there is some penalty methods and like Lagrange multipliers. So just to give you some other, because I won't detail all the different aspects of SOFA, but just to give you some other nice features available in SOFA. For GPU computing, so SOFA is compatible with CUDA, namely just based on a template mechanism. You can relatively easily change your simulation, CPU simulation, to a GPU version of your computation. Many of the codes available in the public version are also implemented in CUDA. So as I said, yeah, all the key components, and I'm no use to say that it's for performance purposes. Python, that's now maybe not so new, but it was new for us, and that was a big change in SOFA 1 year and a half, 2 years ago, I think. 3 years ago, it was yesterday. And so that's a very nice functionality which enables you basically to use the components already implemented in SOFA in C++, but without writing a line of C++, you will be able to describe your scene using Python, and on top of that, to make on-the-fly modifications. So to add, for example, dynamically object in your simulation using Python. So that's something very, very powerful. I think there will be examples later in the example of application using SOFA. You will see, I think, many examples that are, even if you don't see it, based on the Python implementation available in SOFA. And you have many additional plugins. For example, the image plugin that enables to manipulate, so first import, manipulate, and so on medical images, and compatibility with different haptic devices. So that's, I would say, the first. So I don't know if it was intense or not, but basically it's the first rough presentation of what is SOFA, the big picture. Then we will go maybe a bit more into details with different applications this afternoon. So that what you need to remember, it's really the main advantage of SOFA would be its modularity. You have several models available. These different representations that you can use in the same time in the simulation. A wide range of algorithms and solvers also in the framework. Targeting, so always in a purpose of efficiency, and as I mentioned, this GPU compatibility using CUDA computing, yeah, the CUDA, how do you say? I don't remember the word. It's okay. Basically, yeah, the CUDA version of the codes. Today, so far, it's more than 750,000 lines of C++. It's way too big, actually. We are going in the future to make it maybe a bit lighter and more understandable, maybe from people that have never used SOFA before, and cross-platform. It's mainly, I mean, outside from the teams, it's most often used for fast prototyping. And also, as I said, due to its high modularity and the efficiency of the simulation. So what I can tell you is just download it, experience it, and then create your own simulations. And do not hesitate. So to publish, I think I won't have to push you to publish, but just to contribute to SOFA, do not hesitate. There is a website where you can ask all the questions you want, and we'll try. We are trying actually to answer as quickly as we can and as accurately as we can. And yeah, So that's for the first, I would say, theoretical, if you can say that, theoretical part about SOFA. If you have any question, do not hesitate to ask them.